When dealing with multiple buildings fed from a single service, it's crucial to understand how to properly ground each structure. Considering the use of PVC conduit to prevent continuous metallic pass, the approach involves treating each building as a separately derived system. This means each building needs its own grounding electrode system, ensuring safety and compliance with electrical codes. Here's a detailed explanation of the steps involved. Firstly, routing conductors and the neutral conductor to each building from the building service disconnect using PVC conduit is essential. This avoids unintended ground loops and ensures isolation between the electrical systems of each building. Secondly, at each building, a grounding electrode must be installed. This electrode should be a ground rod, typically made of copper-clad steel, and must be at least 8 feet long. The purpose of this electrode is to provide a direct connection to the earth, offering a low impedance path for fault currents. Thirdly, bonding the grounding electrodes together is important. Use a minimum of number 6 American wire gauge copper conductor to connect all the grounding electrodes. This interconnection creates a common grounding system, ensuring that all buildings are at the same ground potential. Fourthly, the neutral conductor needs to be bonded to the grounding electrode system. This bonding should occur at the building service disconnect. Again, a minimum of number 6 American wire gauge copper conductor is required for this connection. This bond establishes the reference point for the electrical system and helps to stabilize voltage. Fifthly, bonding the water pipe and building steel to the grounding electrode system is necessary. This step involves connecting the metal water pipe and structural steel of each building to the grounding electrode system. A minimum of number 6 American wire gauge copper conductor is used for these connections. Bonding the water pipe and building steel ensures that these metal components are at the same ground potential as the electrical system. This minimizes the risk of electric shock if a fault occurs. Now let's delve into some additional details and considerations. The National Electrical Code, specifically Article 250, provides comprehensive guidelines for grounding and bonding. It's crucial to be familiar with these requirements to ensure code compliance. The size of the grounding electrode conductor, which connects the grounding electrode to the service equipment, is determined by NEC Table 250.66. The size of this conductor depends on the size of the service entrance conductors. Make sure to consult this table to select the appropriate conductor size. When driving ground rods, ensure they are installed at least 8 feet in the ground. If rocky soil prevents driving the rod to this depth, it can be buried horizontally in a trench. In cases where multiple ground rods are used, they should be spaced at least 6 feet apart. This spacing helps to minimize the overlapping of their effective grounding zones. Water pipe electrodes must be supplemented by an additional electrode, such as a ground rod or ground ring. The water pipe itself must be in direct contact with the earth for at least 10 feet to qualify as a grounding electrode. The bonding jumper connecting the water pipe to the grounding system must be sized according to NEC Table 250.102. Building steel can also serve as a grounding electrode if it meets certain requirements. The steel must be permanently connected to the earth and must be at least 10 feet in length. The bonding jumper connecting the building steel to the grounding system must be sized according to NEC Table 250.66. In addition to the grounding electrode system, each building must have an equipment grounding system. This system provides a low impedance path for fault currents, helping to trip over current devices and clear faults quickly. The equipment grounding system includes equipment grounding conductors, which are typically green or bare copper wires that run with the circuit conductors and connect to the metal enclosures of electrical equipment. These conductors are sized according to NEC Table 250.122, based on the rating of the overcurrent device protecting the circuit. Bonding is a critical aspect of the equipment grounding system. Bonding involves connecting all metal parts of the electrical system together, including metal conduits, enclosures, and equipment frames. This creates a continuous electrical path, ensuring that all metal parts are at the same ground potential. Bonding jumpers are used to connect these metal parts together. The size of the bonding jumpers is determined by NEC Table 250.102. Ground fault circuit interrupters, or GFCIs, are an important safety device that can help to protect against electric shock. GFCIs detect ground faults and quickly interrupt the circuit, preventing dangerous current from flowing through a person's body. GFCIs are required in certain locations, such as bathrooms, kitchens, and outdoor areas. Surge protective devices, or SPDs, can help to protect electrical equipment from voltage surges caused by lightning or other events. SPD diverts surge current to ground, preventing it from damaging sensitive electronic components. SPD should be installed at the service entrance and at sensitive equipment locations. Regular inspections and testing of the grounding system are essential to ensure its continued effectiveness. Ground resistance testing can be performed to verify that the grounding electrode system is providing a low impedance path to ground. Continuity testing can be performed to verify that all bonding connections are intact. In summary, properly grounding separately derived systems in multiple buildings involves several key steps: routing conductors in PVC conduit, installing grounding electrodes at each building, bonding the grounding electrodes together, bonding the neutral conductor to the grounding electrode system, and bonding the water pipe and building steel to the grounding electrode system are all crucial for safety and code compliance. Remember to consult the NEC and other applicable codes and standards to ensure that your grounding system meets all requirements. This careful attention to detail will help to protect the buildings and their occupants from electrical hazards. Furthermore, consider the specific soil conditions at your location when selecting grounding electrodes. Soil resistivity can significantly impact the effectiveness of a grounding system. High soil resistivity can require the use of additional ground rods or other grounding enhancements to achieve the desired grounding resistance. Soil testing can be performed to determine the soil resistivity at your site. Also, be aware of the potential for corrosion of grounding electrodes. Soil conditions such as high salt content or acidity can accelerate corrosion. Using corrosion-resistant grounding electrodes, such as copper-clad steel or stainless steel, can help to extend the lifespan of the grounding system. Inspecting grounding electrodes regularly for signs of corrosion is also important. When installing grounding conductors, be sure to protect them from physical damage. Grounding conductors should be routed in conduit or otherwise protected from abrasion or impact. Damaged grounding conductors can compromise the effectiveness of the grounding system. Finally, remember that grounding is just one aspect of electrical safety. Other important safety measures include proper wiring practices, the use of overcurrent protection devices, and regular electrical inspections. By following all applicable codes and standards and taking a proactive approach to electrical safety, you can help to prevent electrical accidents and injuries. Also ensure that all electrical work is performed by qualified and licensed electricians. Improperly installed electrical systems can create serious safety hazards. Engaging qualified professionals ensures that the work is done correctly and safely. Consider the long-term maintenance of the grounding system. Grounding systems are not maintenance-free. They require periodic inspection and testing to ensure their continued effectiveness. Establish a regular maintenance schedule to inspect grounding electrodes, conductors, and connections for signs of corrosion, damage, or looseness. Address any issues promptly to maintain the integrity of the grounding system. The location of the service disconnects is also a critical factor. Grouping the service disconnects together near the site entrance, as described, simplifies the overall grounding system. It allows for a central point of connection for the grounding electrode system, making it easier to maintain and inspect. However, ensure that the location of the service disconnects is readily accessible and meets all applicable code requirements. Considering future expansion is important. If you anticipate adding more buildings or expanding the electrical load in the future, plan for the grounding system accordingly. Ensure that the grounding system has sufficient capacity to accommodate future growth. This may involve installing additional grounding electrodes or using larger grounding conductors. Documenting the grounding system is a good practice. Keep a record of the grounding system design, including the location of grounding electrodes, the size of grounding conductors, and the results of grounding resistance tests. This documentation can be helpful for future maintenance and troubleshooting. Also, be aware of any local amendments to the NEC. Some jurisdictions may have local amendments to the NEC that affect grounding requirements. Be sure to check with your local electrical inspector to determine if there are any local amendments that apply to your project. In addition to grounding electrodes, ground rings can also be used as part of the grounding electrode system. A ground ring is a bare copper conductor that is buried in a continuous loop around the perimeter of a building. Ground rings can be effective in providing a low impedance path to ground, especially in areas with high soil resistivity. When using ground rings, the conductor should be buried at a depth of at least 30 inches and should be in direct contact with the earth. The size of the ground ring conductor should be determined according to NEC Table 250.66. Another type of grounding electrode is a concrete encased electrode, also known as a UFO ground. A concrete encased electrode consists of a bare copper conductor that is encased in concrete. This type of electrode is typically installed in the footing or foundation of a building. Concrete encased electrodes can provide a very effective grounding connection, as the concrete helps to protect the conductor from corrosion and maintain good contact with the earth. When using concrete encased electrodes, the conductor should be at least 20 feet in length and should be encased in at least 2 inches of concrete. The size of the conductor should be determined according to NEC Table 250.66. Lightning protection systems are designed to protect buildings from damage caused by lightning strikes. A lightning protection system consists of air terminals, conductors, and grounding electrodes. The air terminals are installed on the roof of the building and are designed to intercept lightning strikes. The conductors carry the lightning current to the grounding electrodes, which dissipate the current into the earth. If you are installing a lightning protection system, it's important to ensure that it is properly grounded. The grounding electrodes for the lightning protection system should be separate from the grounding electrodes for the electrical system. This helps to prevent lightning current from entering the electrical system and damaging equipment. The grounding electrodes for the lightning protection system should be sized according to the requirements of NFPA 780. Standard for the installation of lightning protection systems. Also remember, using PVC conduit is excellent for preventing unintended ground loops between buildings, but it's paramount that all grounding and bonding requirements are meticulously followed to ensure a safe and effective electrical system.